There are other greedy methods that look at different ways of selecting features, such as forward selection and backward elimination. So the way forward selection would work is we assume that first of all we have no variables in a subset of variables that we are selecting, and we will add variables one by one until some accuracy level has been reached, or a number of variables that maximum number of variables that we want to include has reached. So let's say we have x1 through x100, we have 100 different variables, right? And initially we say that your subset is empty. Okay, there is no variable in it. Okay, so then for I is equal to 1 to n, which is, let's say, less than equal to 100, what we will do is we will measure the marginal utility. Sorry, we'll have another loop in here. So let's say your selected subset is phi and your reserve subset is x1 through x10, x100. So this one has all of these. Sorry, it's a set. Okay, so what we are going to say is that for j in or xj, let's say xj in R, in the reserve subset, measure the marginal utility of xj being included in the machine learning model. Okay, so once we have done that, then what we will do is include xk with the largest marginal utility into S and take it out of R. Okay, so basically we are moving one by one variables from R to S, and each time we are finding the one that has the largest marginal utility and we are moving it to S. And backward elimination works the opposite, where S starts with all the variables and R starts with no variable, and we eliminate the ones that has the least marginal utility of if it is eliminated from the machine learning model. So now the disadvantage of these methods is that they look at if you look at forward selection, let's say we are looking at a variable xi, and xi by itself is not very useful unless it is interpreted with xj, and xi and xj together are very useful, but we will not be able to find that when we reach xi if xj is not already in the selected subset S. Okay, so that actually is one of the disadvantages. And in backward elimination, you are starting with a very large model and then you are trying to reduce variables, which can lead to instabilities because there could be a lot of correlated variables already in S, because we start with S having all the variables, and because of that the elimination process may not be very useful. So both of these are greedy methods and they have their disadvantages, but they can work in some cases. And finally, let's look at some tightly linked models, where the embedded models, we already know what is Lasso. So in Lasso, basically now we are looking at W1 and W2 space. Let's say there are two variables, right? And if we didn't have any penalty, if we were just minimizing, let's say, mean square error in regression, we may get contours of mean square error that look elliptical like this. And when we put another term in the optimization, which is minimizing some constant times the L1 norm of weights, we will get these 45-degree tilted squares for different values of the penalization, right? Then what happens is that for certain values of certain combination of that penalty, we will have these these contours that will graze tangentially to this tip, the corner of one of the squares, and because of that we will have elimination of that variable. And this story can unfold in large dimensions also. So basically if we are looking at that penalty, right, so basically we have error term. Okay, so your loss of weights is equal to some error based on the weights plus lambda times L1 norm of W. Right. So if I look at no lambda, then basically I have zero error. If I have large lambda, then I have basically weights are zero. So if I plot 1 over lambda, right, or log of 1 over lambda or 1 over lambda, and I look at the mod of the weights of single weight at a time, right? So for no lambda I will have large weights, and as I keep increasing lambda the weights will decrease and some weights will become zero. Okay, some weights will become zero earlier, some weights will become zero later, right? And but eventually all of them will become zero. So depending on different values of lambda I will have different surviving weights, right? And those surviving weights will be the ones for which the features have not been eliminated. Okay, so in Lasso, by changing lambda I can do both estimating the ML model, which is a whatever is in EW, which could be a linear regression model or a logistic regression model depending on the problem, but I can also do subset selection. And same thing I can do with something called elastic net. In elastic net we will have a second term, right, and that second term would be, let's say, lambda 2 times the L2 norm of W. And what that does is it actually has a certain desirable property where it will keep correlated variables either in or out of the model together. So let me give you a motivating example. So let's say we have two variables x1 and x2 and they're exactly the same, right? And ideally what we would want is we would want w1 x1 plus w2 x2, okay, plus w3, or let's say w1 x1 and w1 x2. I'll tell you why the two are the same, and then w3 x3 etc., right? So because they're exactly the same or they are highly correlated, then I would want their weights to be the same. I wouldn't want one weight to be very high and the other weight to be very low, because then there is an ambiguity. The same effect we can get by having w1 plus alpha times x1 plus w1 minus alpha. Now these become w1 w2 in some sense, x2 plus w3 x3. These two models are exactly the same, provided that alpha does not change the sign of w, right? So between these two, right, the L1 norm of both of these sets of weights is exactly the same, but L2 norm is lower for the first model than for the second model. So even if w1 is 0, right, if x1 is eliminated, it should also take x2 with it, because it's actually the same variable or a highly correlated variable. So either both x1 and x2 should be in the model with a non-zero coefficient, or both should be eliminated from the model with zero coefficient. So that can only be done so that elimination happens because of L1 penalty, and the behavior that they stay together or their coefficients are equal happens because of L2 penalty. L2 penalty is large for the second model and small for the first model. So if we minimize an additional term, then we will have that grouping behavior, which is called elastic net. Similarly, in SVM, instead of looking at L2 norm on the weights, we can also look at L1 norm on the weights. So what is an SVM penalty? So the regular SVM is an L2 SVM. So you will actually find another terminology where L2 is used for something else. It's used for square of the xi, the slack variables. But basically what you have is mod of W2 square, right? All right, and then you have plus some c times sigma of sigma of 1 minus ti, right, yi. And plus, right? So here we are shrinking that L2 norm on W, right? Instead we can have an L1 SVM where we have mod of W. We have the first norm of that, and the second term remains the same, whatever is the hinge loss. So this is your hinge loss. So what this does is that for some penalty, so here you can have lambda, and you can get rid of this. So here you can have lambda here. So for some value of lambda, you will have certain values of W, certain dimensions of W to be 0, and that will effectively eliminate those features. Where is W here? W is absorbed in Y here. Right? So that is one way of doing it. So that is what I mean by L1 SVM here. In some publications, you will see that L1 SVM, they call this particular term to be L1, and when they take the square of the term inside the bracket, they call it L2 SVM. But that's not what I mean. What I mean by L2 SVM is the L2 norm of the penalty on the weights, and here it is going to be L1 norm, which will lead to elimination of some variables. So this is another embedded method, quite similar to the Lasso method, but instead of logistic regression, we have the hinge loss. Okay, hinge loss on each of the samples. And the final method that I will talk about for reducing features is principal component analysis. We will reserve the math for a later class when we actually look at unsupervised methods. But basically what it does is, let's say if you have two different variables, x1 and x2, right, and they are highly correlated such that we can actually draw a line, and that line contains most of the variance of x1 and x2 taken together, and its normal line has little variance, which can be thought of as noise. Then finding this line, basically some linear combination of x1 and x2 will give you that space, will give you that composite variable that captures the essence of x1 and x2 taken together. Right. So basically what we do is we take the covariance matrix of x1 and x2. First we centralize them, we subtract the means from them, we take their covariance matrix, and we try to find the eigenvalues, the eigenvectors corresponding to the highest eigenvalues, and then we reproject the components, the two variables together onto that eigenvector, onto a single eigenvector. So in n dimensions we will use d dimensions, which is less than n, and so that we can reduce the number of variables that we will feed into the machine learning model, although each of those dimensions capture contribution from all the underlying dimensions. Okay, so it's not variable elimination, it's just dimension reduction. So that's why I'm not talking about it now. We will talk about it later. This is just for the relation between these two. So with these feature reduction methods, especially with L1 penalty, elastic net penalty, and there is a more advanced penalty called scarred penalty, you can actually even deal with problems where the number of dimensions is more than the number of samples. So those are called high dimension, low sample size problems, and they are very common in bioinformatics, in gene microarrays, where you are looking at 10,000, 20,000 genes, but you have only a few hundreds of patients, and you are trying to classify them into survivors and non-survivors for cancer. Then you will need a lot of variable reduction, and for that you can use some of these techniques. Thank you.